Hello, students. I got a couple questions on 8.2. So I'm going to post them here. And we've got 8.2, number 3 and number 9. So let's take a look at number 3C. They said number 3C. Okay, so I got to move to the next page. 3C. Got it. Okay, 3C. Oh, okay. Well, let's take a look at this one. Again, honestly, it looks pretty complex. Maybe even a bit scary, right? That's maybe your first instinct is, oh my God, I'm not doing that one. But just pause, take a moment. And the reason you want to take a moment is what in here is making it look scary? Is it the square root of 3? Okay. Well, why don't we just call that W for now? Or something like what, right? So there's a W. So now when I rewrite this, I have 5 times 2x minus W minus 7 times 2x minus W equals 2W. Okay. See, now it's not that intimidating anymore. Again, it's just a number. It's a number that is irrational. That's why we don't write it as a decimal number, because we want to preserve the exact value. But now we can use the distributive property. Distributive property says go ahead and distribute multiplication across addition or subtraction. And let's see what we end up with. So hopefully you get 10x minus 5w minus 14x's plus 7w, and that's going to equal 2w's. Okay. Let's see here. Maybe, I don't know, which way do I want to go? Do I want all the w's on one side, all the x's on the other, maybe? Okay, so let's do a little cleanup first, right? On this side, we've got negative 5w plus 7w, and I've also got 10x's, but I take away 14x's. Okay, so as you're looking at that, then 10x's minus 14x's would be negative 4x's, and a negative 5w or minus 5w, but I add 7w, those will kind of eliminate, leaving me plus 2w. So this is where I'm at now. Now, again, we can use the addition property of equality. So we can add something to both sides. You could add a negative 2w, or you could think of it as being subtraction, but really addition is all we need here. And so this gives me negative 4x because the 2w minus 2w, the 2w minus 2w gives me 0. And then just finish this one up by dividing by negative 4. And that should take care of it because now x is 0. Now, if you plug it back into the top, you can check yourself, even with that square root of 3 in there. So this would be, anytime I see x, I'm going to put in 0. So this becomes 5 times 0 minus the square root of 3 minus 7, and that's 0 minus the square root of 3. And that's supposed to equal 2 square root of 3. Let's check. This becomes minus 5 square root of 3 plus 7 square root of 3. Now, if you notice, that's exactly what we had over here. It just looks different because I got tired of writing the square root of 3, or maybe that was intimidating. So I just changed the way it looked for now. In this situation, it completely eliminated. But if it didn't at that point, maybe it was 2w plus 2w, then I would just write 4 square root of 3 right here. Okay, because there'd be 4 of them. But I'm not going to worry about that right now because I've got this, and I want to see, is this equal to 2 square root of 3? And you can see 7 somethings minus 5 somethings is 2. So it checks out. So there we go. That is how we can do part C. And let's see here. I think the other one the student said was question 9. Question 9. Okay, how to set up the equation was the question, not how to solve it, but how to set it up. All right, so let's think through this. First thing, I mean, as you know, this class is a whole lot of thinking, sometimes more thinking than doing. And there's actually been some research done that shows really good problem solvers, they do more of the thinking up front than they do of the doing up front. They take a little time to make sure they understand it. All right. Miriam is 4 years older than Richard. Okay, so we're talking about ages here. So maybe just to start, maybe just write something down that says, okay, Miriam, M is going to equal Miriam's age, and we'll say R is Richard's age, or Ricardo's. I got a friend named Richard, so it just popped into my head. Ricardo's age. There we go. Okay, 10 years ago, it was this. Oh, wait a minute. Okay, so pause for a second. Now they're bringing up time, and they're saying go back 10 years. So this is, I'm going to say this is Miriam's age now. Okay, you could say it's Miriam's age 10 years ago if you wanted to, but I'm just going to pick something. Okay, because now before I get to the 10 years, so let me hold on this. Can I get the first part? Miriam is 4 years older than Ricardo. 4 years older. So that means we have to take Ricardo's age and add 4 to get to Miriam's age. Okay, so that gives me an equation because now Miriam is Ricardo plus 4. Okay. Now, 10 years ago, so before I do anything, I'm going to come over here and be like, wait a minute. Now we're not talking about Miriam right now. Now we're talking about Miriam 10 years ago and Ricardo 10 years ago, because that says 10 years ago. Okay, so this is, I could write this down, Miriam's age 10 years ago. And similar, this is Ricardo. Ricardo's age 10 years ago. Okay, so there we go. And now Miriam was 3 times as old as Richard was. Okay, so I mean, Miriam's always going to be older, right? She's older. So now 3 times as old. So I need to multiply Ricardo's age by 3 to get her age. Okay, so that makes sense. So what I'm going to have here is I'm going to have M minus 10. That's her age 10 years ago. And to get there, I'd have to go 3 times Ricardo's age. So there are your 2 equations. You have a lot of options here. You could simplify the one that's in green, the bottom one. Kind of as you simplify that, get the M on the left, the R on the right, and then just use elimination. You could notice that M is equal to R plus 4. Wherever you see an M, you could put in R plus 4, and then you have an equation that has only one variable. So that's another option. So again, a lot of things you could do here. I will let you take it from there. The question was just how do I set it up? And let's see here. I think there was an MC question as well. Let's see. Question 12. Question 12 says a student claimed the equation 2x equals 3y has infinitely many whole number solutions and said she could prove it using ideas from number theory. What type of argument might she have made? Interesting. Okay, well, now notice in an argument, you can remember what an argument is. An argument is a sequence of statements to convince you that something is true. It's not like argument is like 2 people yelling at each other. I guess that is one way of trying to convince someone that you're true, but not perfect, right? So how would you convince someone that this has infinitely many whole number solutions? And again, we talked in number theory about multiples, right? Even common multiples, right? So if you were looking at this, maybe you could figure out a way of rewriting it. Or you could even look at this and think back to what we did with the in class, in class activity with the ratios from chapter 6. And you could say, hey, wait a minute, I could rewrite this to show that maybe get x by itself, x equals, right? Or you could say y equals, get y by itself, and have an equation that has something times x, or you have something times y. And that's the idea here is you could then say, okay, now what does that tell you? What whole numbers could you put in for y? You have to be able to put infinitely many in that would get you a whole number for x. Okay. So again, that's the idea. An argument isn't just, two people are arguing. Typically, an argument, when we talk about it mathematically, is I'm trying to convince you of something. That almost always comes after I make a claim. And so what you'll see is a student made a claim. They claim that this has infinitely many solutions, infinitely many whole number solutions. And if you're a teacher in these situations, whenever a student makes a claim, you want to say, why? Why do you think that's true? Can you demonstrate that that is true? What evidence do you have? How would you show someone? That kind of stuff. Okay. So that's the idea behind an argument when it comes to a student like that. Okay. Right at this point, she hasn't made an argument. All she did is say something. So this is, what if she came up to you, the same student, right? And the student says, oh, an odd number plus an odd number is an even number. Instead of just saying, yes, that's correct, you almost always, if you're watching me in class, I don't always just go, yes, that's it. Oftentimes I say, why do you think that? And the reason that you say that is you're trying to get the student to think through their reasoning. It's not just about the answer, it's about the reasoning. And let me demonstrate that very clearly here. You cannot just look at the answer, right? Here's an example. A student who is learning about reducing fractions, it is very common for them to look at this and to say, I need to find a common thing to cancel. And they will remove the sixes and they will end up with 1/4. Now you will look at their work perhaps and be like, oh my gosh, there's no way that could be correct. But it just so happens that 16 is 8 times 2 and 64 is let's see here, 8 times 8, which is 8 times 4 times 2. And so when you are simplifying 16 over 64 the proper way, you might get 8 times 2 here. You might get 8 times 4 times 2 on the bottom. And then as you go to eliminate, you cancel common factors, which is flopping, and you end up with 1/4. Now, this is where students get really frustrated. You got 1/4 as your answer. They got 1/4 as their answer. And you can and you should mark this top one as incorrect because the student's process is not an appropriate process. You can do the wrong thing and get the right answer sometimes. So you want to be really careful with that when you're in kind of your teacher mode. It's tempting to just say, yes, it's 1/4. And if you want to, you might say, that seems like the correct answer, but why? Can you demonstrate your thinking? Can you tell me why that is the case? In this particular situation, this is a fluke of numbers. Okay. It just so happens that 16 divided by 64 is 1/4. It just so happens that is not always the case. Okay. And you might say, oh, it's just a one-time deal. No, it's not a one-time deal. I think there's infinitely many of these where it works. And here's another one. You love this. 166 over 664. You're gonna love it. Well, maybe you'll love it. I found this very interesting. I started looking into it. How many times does this happen? And kind of thinking how it could happen. And what you end up finding is that you actually have infinitely many times that this could happen. So the student could be right infinitely many times, but their reasoning is incorrect. Okay. So, and you want to see a counterexample? Sure. 15 over 54. Cross the fives off. Does that equal 1/4? No, it does not. 15 over 60 is 1/4, not 15 over 54. Okay. So again, it's important to see the reasoning. Don't ask your student to just do something and get you an answer. The answer is not enough. You'll notice that on my exams. So those of you new to the class, my exams are not just about show me the answer. If all you put down is an answer and it's a 10-point question, maybe I'll give you 1 or 2 points. But without showing me how you got there, I cannot ascertain whether you used a proper approach. And that work that you're doing on a test is your argument. It is you backing up your claim. You claimed it was 1/4. Now you're telling me why. So in this class, it's really, really important to do more than just say, here's the answer. And I hope you take that. If you take nothing else with you, it's that. Ask why. Okay. It's not just how do I get the answer? It's why did that work? And will it always work? All right. I hope that helps. Off you go.